Now let's continue to the final video of chapter 13. This is going to cover thiols and sulfides, some synthesis strategies involving epoxides. So sulfur appears just below the oxygen on the periodic table, as I've mentioned a few times. The thiol group, SH group, is a sulfur analog of an alcohol, therefore. So the name of the compound with SH ends in thiol instead of ol. And so you name the thiols correspondingly. Thiols are also called mercaptans sometimes. The mercapto prefix is used when you are naming SH as a substituent. So thiols have a lower priority than alcohols, obviously, because this is going to be named as an alcohol, and the SH group will be mercapto. So this is 3-mercapto, 3-methyl, 1-butanol. And just something that's interesting here is one that has a useful purpose in medicine. Thiols are known for their unpleasant odor, as you probably already know. Skunks use thiols as a defense mechanism, and methane thiol is what you smell when you actually smell natural gas. You don't smell the gas, you smell the methane thiol. The hydrosulfite ion is a strong nucleophile, but a weak base. It's a strong nucleophile because of its polarizability. HS promotes an SN2 mechanism rather than E2, therefore. Primary and secondary thiols can be synthesized from SN2 reactions of sodium thiolate with an alkyl halide. So here you see the alkyl bromide reacting with NaSH to give you the thiol. Here the same thing. Notice the inversion of stereochemistry because this is an SN2 reaction. They're oxidized, thiols are oxidized to disulfides with bromine under basic condition, and they proceed through the alkyl sulfonyl bromide. You can see the SN2 reaction. First, the S- attacks bromide, displacing bromide, and then you can see another SN2 reaction. This is occurring on sulfur to displace bromide, and that gives you the disulfide. The disulfide can be reduced to the corresponding thiol with zinc metal. So this would, the byproduct here is going to be zinc dichloride, of course. The interconversion between thiol and disulfide can occur directly via a 3-radical mechanism. The bond dissociation energy of an SS bond, so this is a heteroatom bond. It's very weak, as I've mentioned many times. It's about 53 kcals per mole. And so the bond is very easily made and broken, and this what gives proteins the shapes due to the sulfur-sulfur bond. Sulfur analogs of ethers are called sulfides or thioethers. A sulfide can be named as a substituent. So here this is a methoxy group. This is a methyl thio group, as I mentioned earlier. So this one would be 1,1-dichloro, 4-methoxycyclohexane. This is going to be 1,1-dichloro, 4-methyl-thiocyclohexane. So very similar nomenclature rules. Sulfides are generally prepared by nucleophilic attack of a thiolate on an alkyl halide. So S minus does a backside attack. This is an SN2 reaction, and it creates the sulfide. And this, of course, is obtained by deprotonating the thiol with sodium hydroxide, as you saw earlier. Sulfides undergo a number of reactions. An SN2 reaction with an alkyl halide, and the product is a very strong alkylating reagent. You can add an alkyl group to a variety of nucleophiles. So sulfides can also be oxidized to sulfoxides or sulfones, increasing the oxidation. But the choice of your oxidizing agent depends on which one you want to make. How far do you want to go in the oxidation? So sodium metaperiodate will give you the sulfoxide. Hydrogen peroxide will give you the sulfone. The SO bond has very little double bond character. This is a much stronger resonance contributor compared to the carbonyl. So this can be contrasted by the carbonyl, or contrasted with the carbonyl. So this is a stronger resonance contributor, the ionic form. And the same thing over here. This is a stronger resonance contributor, the diionic form, more so than in carbonyls. Because the sulfides are readily oxidized, they make good reducing agents. That's why DMS is used to reduce the ozonide to the carbonyls. And the dimethyl sulfide is converted to dimethyl sulfoxide because the sulfur picks up one of the oxygens. Epoxides allow for installing two functional groups on adjacent carbons. So if you have a nucleophilic attack at one end of the epoxide, the oxygen becomes bonded to the other end of the epoxide. So whenever you see adjacent functional groups, you should think of the epoxide that is made from an alkene as the starting material. So for example, here you would make the epoxide using MCPBA, and then the cyanide could function as the nucleophile, and it will open up the epoxide. And so you would get a cyano-carbon bond formed and a carbon-oxygen bond formed. So you have the alcohol substituent and the cyano group. Notice that this is another example of a carbon-carbon bond formation. So this is one of those important carbon-carbon bond forming reactions that you need to add to your list so that you can remember it. You have very few of these, and this is a way of augmenting the carbon skeleton by one carbon atom. By reacting an epoxide with a Grignard reagent, the carbon skeleton can also be modified. So here you have increased the carbon skeleton by however many carbons you have in the alkyl group. So this is not just limited to just one carbon. It can be however many carbons. You can think of the alkyl halide. The alkyl halide is the starting material, and that is the alkyl group that will be added at one end of the epoxide. So that, as I mentioned, the epoxide yields a longer carbon chain with a functional group on the second carbon atom of the newly installed chain. So if you're taking the perspective of the alkyl group and you want to elaborate on the alkyl group, you can use an epoxide as the reagent, and you will add 2 carbons with a functional group on carbon number 2. If you think of the alkyl group as the skeleton that you want to modify, then you would use a Grignard reagent, and you can use the carbonyl so the Grignard inserts, and then it's added to the carbonyl. So in this case, you extend the carbon skeleton by however many atoms you have on the carbonyl, so that can be varied, but the oxygen is attached to carbon 1. Here the oxygen is attached to carbon 2. So you can see how these two methods complement each other. Now, you may remember that I mentioned to you that this sort of starburst diagram is very good for review. And when I made the preview and review videos, I promised that I would put these in my PowerPoint so that you could print them off. This is the slide that has all of the reagents on it, and this is the slide without all of the reagents. So you can print these last two slides and use them to test your memory and study for the reactions of epoxides. So that concludes this chapter.